So I had the first lecture on Monday, which is now some time ago. So I will start with an extremely brief recap, which starts on page 11. So what we did on Monday last time was that we discussed the kind of necessary theory needed to define a gauge theory, and then we defined the kind of simplest possible gauge theory that you can have, which has the whose probability measure is written up there. So Z was a normalizing function, beta was a parameter, and n was the size of the lattice. And we didn't care too much about the size of the lattice because whenever we calculate something, we can end up with afterwards. So the main thing is that in the exponent of that exponential function, we have something that punishes packets. So we have spins on edges, then we calculate the corresponding two form and punish packets. And when we simulate this in 2 dimensions, it looks roughly like that. So when beta is 0, or regardless of what beta is, you have roughly the same number of packets, and we discussed why. This is with local gauge transforms that made that happen. But what really happens when you increase beta is that the number of packets increase. And we also saw last, and yeah, so increase. So what we then tried to do, and I tried to argue, was that the relevant observable to use was Wilson loops, which is what you got if you pick a nice loop, which is usually rectangular or sufficient to take a rectangular one, and then multiply, so the products there should be sums, because it's inside of the representation. You sum up the spins over the boundary of the loop. And after that, we stated a theorem, which is now stated in a slightly stronger form, because I now assume the group is sent to you. Namely that the expected value of this observable has a phase transition, and it's supposed to go from what's called area law, where the expectation kind of behaves like the area of the loop, and perimeter law when it behaves like the perimeter of the loop. And we also discussed that you are believed to have this type of behavior for essentially all groups. The only thing that might happen is that one of these beta 1 or beta 2, and the one should be infinity. They could be the same, or they are most likely the same, but it could also be that one of them is 0, one of them is infinity, so that you really only see one of the phases. But the goal for today, or what I will try to do today, is to prove that we at least have these two phases when the group is set to. And I will try to do it in a way so that most of the theorem would kind of transfer to all finite groups, because they have roughly the same behavior. So that's the goal for today.
Sorry, so the betas I missed, so they're between 0 and 1? Or
no, 0 and infinity.
Yeah.
And this is because it's a theorem state. I mean, in practice, I think this is still true, that the critical value is in there. So in theory, it's still true. But if you want to state it more generally, you need to be like 0 to infinity and without the strict boundaries, because one of them might be 0 or infinity.
Right, okay.
So the goal today will be to argue, try to explain why something like this should be true, at least when the group is set to. And then the things we want to know about these models, gauge theories in general, depends a lot on how motivated you are by the physics problem and how motivated you are by the math problem. Because from physics, as was kind of discussed with Fika the other day, everything about Z2 you really want to know is kind of known. It's a toy model for the physics model. And what you really want to know for other groups are essentially, first, is there area law and perimeter law? Like, do you have both phases or do you have only one? You can do it for all finite groups. It's known for all finite groups. It's known for U1, but it's not really known for SU of 2, for example. I don't think so. Like, that's the type of group you want to understand properly. And then you might want to know what the decay of correlation is. And what I mean with that is that if you have two distinct Wilson loops that are well separated, how does the covariance decay in the area? And both of these things are known for all finite groups. But then you can ask a bunch of math questions if you are more motivated by math and the fact that you kind of like spin systems, like the Ising model is nice, for example. So you can ask questions that for finite groups are beta 1 equal to beta 2, like do you have a transition directly from perimeter law to area law? Or is there a phase in between? It's believed that the answer is no, and the physics literature strongly supports that they should be the same, but there is no math proof for that. If not, the dimension is 3, because then it's by a paper from last year, I think, so it's very recent. You could ask, of course, as you do for the Ising model, does something interesting happen at the phase transition? That's not known. For d equal to 3, it's not known even what kind of law you have at the phase transition. You could ask about other phase transitions. There are other observables you can think of in these systems. In particular, there's something called the polyacon loop. That should also have a phase transition. And also, if you believe in the analogy with packet percolation, which we will support a bit better later today, packet percolation is known to have several different phase transitions, in particular in higher dimensions. And to some extent, you should see most of them in this model as well. So if you're really only interested in the model, you could look at other things than area law, which is primitive law. You could ask if there could be any limiting models. And also you could ask about what these constants are. So in the theorem, both for area law and primitive law, you have 2 constants, like large c and small c. You could ask what they are and how they depend on data. And that might be important if you're interested in C. So that's the type of things you could be asking. But today, again, the main goal with the same corrections will be to try to argue that this theorem holds, that argue that there should be a region with area law and one region with primitive law. And that roughly means that we need to prove 4 things. So we need to give a lower bound for area law. That's supposed to hold for all beta, to say that the worst possible decay we can have should be some kind of area law. And then we need a corresponding upper bound saying that the best possible decay we could have would be primitive law. That would say that at least the span of the decay rate, but then we need to show that for small beta we actually do have area law, and that for large beta we actually have primitive law. So I will try to give you some argument for all those. So that's the goal. And we will start by the easiest first. And again, there is kind of one simple way to do that. I'll do all this, and we will do that at the end of the lecture. So the ways I present first, that's not the simplest way to do this, but it's the way that kind of extends to other finite groups. So that's the main motivation to do it, and also hopefully it will give you some kind of feeling for how these models work. And the simplest proof will not do that. So first, no, I should not do this. I should use the screen. I wanted to close.
I think you can tell the person who's filming.
Yeah.
Yes.
Or I can do it like that. It's more like brute force. So the first thing we need to do, or the first goal, will be to argue that the worst possible decay we can have is an area law. And actually that's really, really simple. If you have strong belief in the Gini-Breen inequalities. So they are extremely useful in many cases. The simpler version of that is called the GHS inequalities, which also hold for this model, and you will see very soon how it comes in. And you can prove that using the Gini-Breen inequalities, because they are kind of the more general framework for doing that. However, for gauge theories, and also for the Ising model, it's kind of overkill to go through the Gini-Breen inequalities if no one else does it for you, because it's already done, you're fine. Because you can do it by current expansion, and that's much easier, if you know what that is. So first, the lower bound. Which is the easiest one again, because this is really a one-line argument. So what I'm going to try to argue is that the worst possible decay you can have is area law. It can't be worse. And the reason for this is that, again, we're trying to calculate the expectation. We're doing this in a finite box, but you can imagine that is crazy large compared to the side of the box, and we can let that go to infinity afterwards, so it's not a big problem. And we have this observable. Now that observable, by definition, that was the product over all the edges in the loop. And then we're supposed to take the product of the representation of the spin at the edge E. So that is what we're trying to calculate. And here we have no area. But one of the things we're mentioning on Monday was one of the kind of magic things with a discrete exterior calculus, and that is Stokes' theorem. The whole point with Stokes' theorem now is that this expectation can be written in another way. Namely, instead of looking at the loop and looking at the edges in the boundary, you can pick a surface that has the loop as its boundary, and instead multiply over the packets in that surface, which will now be denoted by Q. And then instead you get rho of d sigma of P. And this was Stokes' theorem. It's nice. So, like the main reason to believe this might be good is that we're after an area, and now we have at least something that could have an area. A loop doesn't necessarily obviously have an area, but this surface definitely has an area. And the place where we want to use these inequalities now is to say that this is actually larger than or equal to the product over the packets in the surface. And then here's the expectation of the representation of the differential at P. And now this is kind of good. So this is what falls from either the DHS inequalities or the GUP inequalities. And this part is Stokes' theorem. So the reason now that this is good is that we have a product now over a number of packets. You might imagine that these are different because they are different packets, like we are having a product over all the packets in some kind of surface. But if I take let n go to infinity, they are kind of the same because the relative limit is supposed to be translation invariant, so it shouldn't matter which packet I pick. So if you let large n, so the box size, go to infinity, we get that the expectation of the Wilson loop has to be larger than or equal to, and now we can pick any packet. So we pick a favorite packet somewhere and call it P0. So the expectation of rho of d sigma at P0, and then we have the number of packets in this surface. So let's call that U, just to call it something. Now, you can kind of easily show that this is non-negative or not equal to 0. And essentially that's believable because in the exponent of a Hamiltonian we are really punishing packets. So for this to be 0 would be quite odd. So if you believe that that's not 0, then this would give you a lower bound that's areable. Because now this should hold for any surface. So in particular, if we have a loop, or rectangular loop, we could definitely just take the flat surface corresponding to that, and then we are done. So for that reason, it's kind of reasonable to have a lower bound that's areable. Again, this is not the only way to do it, but it's kind of the nicest way to do it because it's quite clean. And also, I guess there is nothing here, like for this argument to work, Stokes' theorem holds in greater generality, that's really not the problem. You need maybe to worry a bit about whether or not you have the GUP inequalities, and we heard earlier this week that there are settings where you don't, or if you do, but as soon as you have them, this proof works. So in particular, it would hold for any finite abelian group, for example. Do you have any questions about that? So I hope that this convinces you that it should be a lower boundary. So the next thing we need to do is to do the general upper bound to argue that cannot be better than perimeter law. And perhaps that's more surprising because we have many other models where correlations would be like constant or polynomial or something. So to actually have perimeter law is perhaps stronger than you would guess what we have. So the next thing we're going to do is an upper bound, a general upper bound. And this, which is nice for those of you that do kind of discrete probability theory, and perhaps less nice for those of you who are almost doing complex analysis. This is very probabilistic and almost silly probabilistic, but it's to some extent even easier than the one we had there. So again, and this also answers a question from Ellen, which I did answer that well on Monday, namely why we wanted to keep working with the one forms. Because in this proof, the one forms really didn't help. The first thing we did was to go to a two-form and a sequence of packets, but this bound will actually use the one forms. So again, you're supposed to calculate this and you're supposed to find an upper bound. Now, exactly as before, what we're calculating is the product over, or expectation of the product over all edges in the loop. And then we have the representation of the spin at each edge E. Now, this by itself is kind of a mess, and it's extremely messy if you think about it, because you saw the simulations we had. They were kind of horrible if you just look at the edges. They looked extremely noisy. So it's not obvious how to think about this. But one way to simplify this thing is to add another layer of expectations. So inside the first expectation, and this is all with n and beta. Okay, so if I don't write anything, I will mean n and beta. So the inner expectation I want to have is that I'm still calculating the same thing. So the product of the spins at the loop, but I'm going to condition on the set of all spins, right? For E prime not in the loop. And when I say not in the loop, I really mean like not in the loop in any orientation. So this I'm allowed by like basic probability theory.
So maybe the complement of this?
The complement of gamma?
You're conditioning on prime not in gamma?
Yeah, so I'm conditioning on the spin on, or I'm trying to. Maybe I missed something.
So you're missing a little slash. In the
E prime is next to gamma, not belong, I guess.
Ah, perfect. Yes. I mean, I guess it would be true technically otherwise as well, but this is definitely better. So now the reason this is good is the following. So let's draw a picture. So say that this is loop, and I'm going to make it quite small because I really want to continue writing. So this is loops where we have spins. So what I've done now is that I've conditioned on the spins everywhere else. So I know what the spin is here and here. Like I know the values of all other spins. And I'm not going to continue doing this forever. But I really know the value of all the all these purple things. There are no spins. That's bad. Let's see if it solves itself this time. No, so I've done that. So what happens then, if you remember what the measure was, in our measure, the only thing we were worrying about was we had this sum over all the packets, or the product maybe. We had a beta in front, and then we had rho of the sigma of P. So in this conditioning, I already know what the spins are on most edges. Like it will not matter. So if I'm wondering what the spin will be at an edge E, Now almost all the spins here, they occur in many other terms here, of course, but in each time an edge E kind of affects one of those things, all the other edges will be purple, except if we are at a corner, because then, like might have a bucket, that one, for example, where you have two white edges and two purple ones. But for almost all of them, especially for a rectangle, in each packet there will be at most one white edge. So that means that under that conditioning, almost those edges are independent. Like almost all of them, except for a few ones at the corner. So this thing is all a giant parenthesis. So the only edges that might need some special treatment will be the edges at the corners. Apart from edges at the corners, all other edges under that conditioning will be independent. So this is equal to the expectation. And then I could move out this thing, kind of almost, because almost all edges will be independent, except for the corner edges. So let's call them gamma C, where C is the corner. And then I will have an expectation of rho of sigma of E, conditioned on this same thing, sigma of E prime for E prime naught in plus minus gamma. So that's all the non-corner edges, and then I need to multiply by the corner edge thing. So corner edges, and then I have the product over all corner edges, and then exactly the same thing. Okay so far? And this is also supposed to be that. So we have that. What's good now is that, again, I'm after an upper bound. I don't care about the lower bound now, and I don't really care about this being optimal in any way. I just want an upper bound that will be optimal. This is some kind of expectation over the representation of something. The representation was always plus or minus 1. So worst case, and like a rectangular loop has 8 corner edges. So I do not lose too much by simply noting that this is smaller than 1. Worst case. So then I only have this thing left. So I have an expectation of a product of a lot of expectations. So then the question is, is it okay?
Yeah, I was thinking if you have another group, I guess you can still do that.
I guess I could still do that.
So you have this unitarity.
It's always interesting, and also for another group to get a number, it could have to be a trace.
Yeah.
And it's unitary.
Yeah. It's fine.
Yeah, so you could do some kind of upper bound.
Yeah.
So I think I'm fine so far. So then we only need to do this thing. So now we have an expectation of something that's either plus or minus 1. So it should be like 1 times the probability that it's 1 minus the probability that it's minus 1. And we need an upper bound. So we need to think about how large can we kind of make this expectation. And this edge will want to take the spin so that the neighboring packets will be 1. Like that is what it will want to do. So if you think about it for a while, you will see that like the worst or the best possible case, if you want to make it as big as possible, is if all the edges, all the purple edges, have spin 1. Because that makes it as cheap as possible to make it 1. And if it's 1, you will get like a big contribution from the top there. So this is smaller than or equal to. And we could keep the outer expectation just to be nice. We have the product over all edges in gamma at not a corner. And now I claim that that expectation is at most e to them. And now I have to think about what that will be if like all the neighboring spins are 1, because that will be the best case, and that's also 1. And if that happens, I get the contribution of e to the beta something, you have to think about the dimension now. So let's assume the dimension is d. Because then the number of plaquettes that are adjacent to an edge is 2 times d minus 1. And then finally we have both positively and negatively oriented plaquettes. So in fact that's times 2. So that's the weight you get if all the neighboring plaquettes are 1. In the same situation, the probability that you get a negative 1 would be e to the minus the same thing. So minus now 4 beta e minus 1. And then you need to normalize. So e to the beta 4 beta. Plus e to the minus 4 beta e minus 1. And this is now really nice because this is just a number. It's some kind of number. It's really not good, but it's just a number. So the expectation here is very meaningless. And this is also the same for all the edges. So if we call this something, say C, or alpha or something. Alpha is nice, maybe. No, alpha is not nice. Let's call it A. Then what we just wrote is in fact A to the number of edges in there. So gamma, all the edges that are not corner edges. So this is essentially the length of gamma. We have lost something because we have lost the corner edges. And you could do them as well if you were more careful. But if you have a rectangular loop, the number of corner edges do not grow at all with the size of the loop, so this really is pretty low. So the main thing that is slightly tricky here is to convince yourself about that this is actually like the worst possible, the best possible situation. But on the other hand, it's not very important because you could imagine that there is some situation you could just take the worst over all possible allocations and then get something. So that would be fine. So it's definitely a number. So if you're not convinced that it's not that number, that's kind of fine because it's definitely a number and any number would give the same thing. So that will give you an upper bound of perimeter. And again, this is not optimal by any means. It's actually quite bad. It's a upper bound, but it's a quite bad upper bound. And also, as we saw on Monday, if you're in 2 dimensions, then you're not supposed to have perimeter law at all. You're supposed to always have area law, and then this is kind of particularly bad, because then having an upper bound that's on the completely wrong order is of course bad. But it's not at all obvious, like, where in the proof this becomes so much worse in 2 dimensions. So I mean, the main point is this is not a good upper bound in general. It's just good if you have a matching lower bound. But at least in dimensions 3 and higher, this is kind of so now what remains is to do the 2 other bounds, which are the more complicated ones. So we need a lower bound perimeter law that should be good for low beta in the load, or high beta, large beta, so in the low hyperpurity. And we need a upper bound that gives area law for small beta. So that's the 2 parts that kind of remain. But before we go there, I want to start the slides again. So let's see if this magically works. If I wait. Soon. It will work pretty soon. Yeah. So what we haven't done so far, so there are 2 bounds missing, and also what we haven't done so far, that will be kind of the next thing, would be to argue somehow like why there should be difference between 2 dimensions and 3 dimensions. And if you remember, all the simulations you saw in the beginning were in 2 dimensions. But there should be some proper difference between 2 dimensions and 3 dimensions. And in particular, there should be some kind of difference that will be crucial in the other proofs, because now we need to prove that we sometimes have perimeter law, and that proof should somehow fail in 2 dimensions. So there must be some kind of difference. And the main difference is caused by something called vortices, which is kind of confusing because Christoph learned a bit about vortices in the morning, and that's also called vortices, but it's something completely different, or kind of different. You didn't give the definition, so it's very easy for me to say that they are very different, but they are slightly different. So the idea of vortices comes from thinking about how you can make 2 forms from 1 forms. So of course you can pick any edge configuration, and then you can check what two form you get, and most likely there will be kind of a lot of buckets. Like no matter what beta is, you will get a lot of buckets. They might be very spread out, and the density might be very low, but you will get buckets. But you could also start from the other direction and think about, like, if I just pick a really, really simple edge configuration, like what kind of really simple bucket configurations can I have? How do 1 forms correspond to 2 forms? And the simplest possible thing you could do in 2 dimensions would be to just add 1 edge and see what happens. And in 1 dimension, each edge is adjacent to exactly 2 buckets. So what would happen then is that, well, those 2 buckets would be present, and you would have no other buckets. So that's kind of nice. You could do that in higher dimensions as well. That's to the right, that's in 3 dimensions. You could add 1 edge and see what happens. And in 3 dimensions, each edge would be adjacent to 4 buckets. So the 2 form will have supporting 4 buckets. If you don't only count the positively oriented ones. So like at that point, there is no really, really big difference. So the big difference comes if you start looking at more than 1 edge. So in the example below the top one, I do 4 edges. So then think of a 1 form that has support in exactly those 4 edges. What you can do then in 2 dimensions is that if you look at the 2 form, so remember that we started with a 1 form. And as Christoph reminded you of this morning very briefly, that was essentially some kind of function on the edges of Z2 or Z3 or whatever you have, with the property that if you look at the spin on an edge, it would be the opposite as the spin to the negative oriented edge at the same place. So if you start with the 1 form sigma, and in particular if we assume that the group is Z2, then d sigma, the differential at a bucket, that was the sum over all the edges in the boundary of that bucket, and then sigma of E. And if the group is Z2, this will be 0, like the sum of the things in Z2 is 0 if there's an even number of ones. So either no ones, 2 ones, or 4 ones. So if you look between these red lines, each of those buckets has exactly 2 red lines in its boundary. So they will not, like the corresponding 2 form will not have support there. The only place where it will have support will be kind of at the end points of these 4 lines. So that means that you can have 2 forms, so that you can find like spin configurations which give you support in 2 buckets, but they can be very spread out. So it's a bit like in the XY model, you can have these vortex and anti-vortex that are very spread out. The problem with that is that if you just have a very complicated spin configuration, you cannot really distinguish which buckets kind of belong together because they are very spread out. However, if you go up in 3 dimensions or higher and have some number of edges and look at all the buckets that cause, they will always kind of stick together and form, to some extent, connected set of buckets. If you think about buckets being connected if they are in the same 3 cell of lattice, so the same 3-dimensional cell. And that makes a huge difference, because in 2 dimensions then you can't really, like if you see a bunch of plaquettes, you can really say very little about the one form, or almost nothing, because they can be caused by a lot of different one forms. And you can't say anything about which plaquettes like belong to each other in any way whatsoever, because there is no geometry to be found. Whereas in 3 dimensions and higher, you will find these kind of clusters of plaquettes. So that's a major difference. And if you usually think about duals, in 3 dimensions, if you think about the dual of those plaquettes, they will form something closed. So the dual of plaquettes in 3 dimensions would be lined, so the top one would correspond to kind of a closed circle, like a square, and this one, the dual of that, would be a rectangle. So since a dual is always, in 3 dimensions, a closed curve, it has to be something that's kind of connected, whereas the boundary of something in 2 dimensions can be two things very far apart. So this is a phenomena that you see in dimensions 3 and higher, that plaquettes kind of cluster together, and you don't see that at all in dimension 2. So that's the main geometric difference. And that's also what's motivating the definition of vortices. So as soon as you see a connected component in the 2 form of plaquettes that are assigned spin 1, you call that a vortex. And again, we say that 2 plaquettes are connected if they are in the boundary of some common 3 cell. And the 3 cell then is like a regular cube. So in 3 dimensions higher, we can talk about vortices, and that might be a thing. In dimension 2, that will not be a thing. So that's a big difference. Another tool, which will be very useful when we talk about these things, is something called the Poincare lemma. And of course, there are a lot of lemmas called the Poincare lemma in different parts of math. But the one we will use here will be the one which says that, and I will write it so that we have it for later. That if you have a 2 form that is closed, so it's caused by 1 form somehow. Doesn't really matter. It's a discrete differential of a 1 form. So if you see a 2 form, and formally you would write it like you see a 2 form in your box. Group is Z2, but this works for many more groups than Z2. And you need 2 things. Maybe I should write it comma. First, you need that it's actually closed. What that means is that it could be caused by 1 form, or is caused by 1 form. So you need that. And mu has support in a finite box B. So now B is a box and Bn is our crazy large box. So think of nu as being something small, like the set, a clump of plaquettes you see somewhere in the configuration. Then there is a 1 form, sigma, which has support only inside this smaller box, or perhaps just the edges outside. With the sigma is equal to mu. So this looks like a very technical thing, but in fact it will be extremely useful later. One of the reasons this is extremely useful is that it will allow us to, when the beta is really large, then you should expect to see very few plaquettes in general, because big beta should suppress plaquettes. They still appear as kind of these clumps or clusters, but now these clusters will be hopefully kind of small and spread out. And if they are small and kind of spread out, we will most likely be able to put like boxes around them. And then we can use this lemma to translate that back to 1 form. So this will be another instance where we actually need the 1 forms. So that's called a point clear lemma, and that's one of the tools we'll need in the perimeter law proof for that to work. So now I'm on the slides again. Sorry. Yeah, it works. So as soon as the display is on again, I will show you different simulations, because the previous simulations I showed you were in 2 dimensions. But now we know that this vortex thing should exist in higher dimensions, so it's worth looking at the simulation of higher dimensions. So now to the left is a simulation we saw Monday and before, and here I think beta is 2.2, so it's not like crazy large. And then we said that the edges doesn't really show much of a pattern. Like you could look really closely and calculate how often you see a plaquette with an odd number of things and so on. But it's kind of noisy. And if you look at the squares, they are just spread out in some kind of random pattern. There's no way to pair them as you do for the XY model. But as soon as you go to higher dimensions, and here I didn't draw the edges because that would have made it a mess, you see that you really get these small clusters of plaquettes. And this is in 3 dimensions, and I picked beta quite large. And you can see that almost all the clusters are of this like smallest possible form, that is 4 plaquettes kind of around an edge. So that's the most common structure to see. I think there is 1 or 2, there's one there which looks really, really strange, but I think that's because it's like at the boundary of the simulation. And there is one there that is actually of like the next smallest size up. But otherwise most are of the smallest size of the simulation. So that's kind of a big difference, and this is also why you should expect the model to possibly behave differently in the different dimensions. So the low temperature phase, when beta is large, that's when we expect to see perimeter law. The idea of that will somehow be to use that picture, that we have very spread out vortices that do not interact very much. And if you want to be close to the phase transition, then you should expect these clusters to grow, and sooner or later this picture will kind of break because they will start be so large that you can separate them anymore. But the proof we'll do will be in the phase when these are kind of smallish and well separated. So the next thing we are going to need to make that picture slightly better will be some kind of just upper bound for how large clusters can be. So now we can turn the slides off again. Perfect. So again, vortices are these type of clusters that could appear in the configuration. And what we kind of want to do is that we want to have some kind of upper bound on how large they typically are. It's not exactly obvious what that question means. So to make it slightly more precise, we will ask about the probability of seeing a vortex somewhere of a certain size that intersects a particular plaquette. It's to kind of root it somewhere, because otherwise it's not obvious what the question means. So before we do that, we will do a lemma. Let's call it lemma. Which says something about how likely it is to see a particular vortex at a particular place in your spin configuration. I mean, if the vortex is very large, that should be quite unlikely, but you can imagine that like seeing a small one might actually happen. So we will try to give some kind of upper bound to the probability, and now this is with respect to the same probability measure as we always use. So the probability that nu, some kind of particular nu, is a vortex in E sigma. And what that means is that at the plaquettes where this has support, they kind of agree. And it's not that in this configuration the vortex could have been bigger, it's really like this one that you see there. So we need to upper bound this somehow. And there's essentially one way to do it. Like there are 2 ways to do it. I know 2 ways to do it, because Chatterjee does it another way in his paper. because an upper bound like this in the recent years first appeared in Soraf's paper from I think 2016, or it was published in 2016, about Ising lattice gate theory. And he had a lemma like this and used a dual model to get it. And we're not going to do that proof, even though Christoph has introduced duals in Lattice, because it's much longer. And this proof is similar to what you usually see for the Ising model. So our probability measure, the only one we have, is coming from these Gibbs measures. You sum over all the spin configurations, and then you have e to the beta, sum over all packets, rho of the sigma of p. That is what we do all the time. And now I want to sum over all the spin configurations so that nu is the vortex in d sigma. So let's write that as like nu is smaller than or equal to d sigma. You don't have to write that all the time. Meaning that that appears in d sigma, and d sigma doesn't like have a larger vortex at the same place. It's really that vortex. That's really the connected cluster you see at nu. And then we need to divide that by the set of all spin configurations and the weight. So we have that. This is really just what you get if you write down the probability in terms of the Hamiltonian. So we need an upper bound. And there's essentially one thing we need to do. So the first thing we're going to do is to do what Ellen kind of suggested on Monday again. This is defined on one forms, and it turns out you can kind of equally well define the model on those two forms. So let's just do that. Okay, we do that. So that means that instead of looking at one forms, so that here sigma is really in omega 1, we can equally well look at omega in like two forms that are closed, meaning they arise from some kind of one form. It's not obvious this will be the same thing, but it will turn out to be the same thing. And then in the numerator, we will still want nu to be smaller than or equal to omega, so that nu is the vortex in omega. And then we have this thing, p of, and now I can just write omega of p. It makes it slightly easier. And then exactly the same thing down here, except for this extra condition. So just sum over all two forms that are closed. And the same thing. So that didn't really help much, like not for real. We're suddenly working with closed two forms instead. So to get an upper bound for that, we need to do a trick. And the trick we will do is the following. So this will be some kind of parenthesis. If
Sorry, I missed one thing. So for the flat two form,
yeah,
yes, sorry, it's closed now.
it's closed now. Yeah, if it hadn't been closed, I would be in big trouble, but it's closed. Yes.
What does the inequality mean?
It just means that, so what I wanted to say is that nu is a vortex in omega. So if you think of omega now as being, having all these kind of small clusters somewhere, so assume this is omega, this is omega. And nu is simply one vortex, so it could be, for example, this one. So I'm summing over all closed two forms that agree with that vortex exactly there. Outside it can do other stuff, like it can have big vortices and small vortices, but there it's that vortex. So that works. Did I answer your question? Good.
For each omega, there are many sigma configurations.
Yeah, there's a lot of ones. So it's not obvious that I can pass from one form to two forms. That really follows again from the Poincaré lemma if you state it somewhere more strongly, because it also says that for each closed two form, or each closed two form corresponds to as many one forms. Like, so this is like m to 1 math or something like that, where m is a number you can calculate if you wanted to. So now we have this. What I want to use is that if omega is closed, that exactly means that. Nu is a cluster, so that means it's some kind of clump of plaquettes and there are no other plaquettes kind of nearby. It kind of means to show that that implies that it must satisfy this. So it must also be closed. Now if they are both closed, and everything is linear, because that's the nice part with this is that everything is linear. Then if you look at omega minus nu, that will also be closed. That's kind of a nice thing. The other thing that's nice is that this is minus, and it's not a complicated minus, it's really just minus. So if you think about the map, omega maps to omega minus nu, that's really a one-to-one map, it's a bijection. Because it is minus, and nu is fixed. So these are kind of the good things we need. So I want an upper bound for this. So it doesn't matter if I make the denominator smaller. It will just make the whole thing bigger, right? So I will keep the numerator. So all two forms, I'm solving over two forms that are closed, and which contains this special vortex that I like. And I will keep exactly the same thing as we had before, but I want to divide by something that's actually smaller. And the way to do that is that I will now use exactly the same sum as I have up here. That will make it smaller. So this condition I didn't have in the denominator before. I've added that. That will certainly make the sum smaller. But if I divide by the same thing now, I will kind of be in trouble because then the upper bound will be 1 and that will be really boring. So I need to do something else. Now I will use it by bijection, because before I would have a beta sum over all plaquettes, and I would just have had omega there. Now I will instead use the bijection and have omega minus nu of p. And I need one more time. So now the sums are exactly the same, and two things have happened. First, I added that thing, and if I had kept everything else the same, I would have divided, like gotten something by itself, and that would have been 1. But I also did that. So what that means is that now in practice in the denominator, I'm summing over all the two forms that are equal to 0 at that vortex. That's essentially what they're doing. So they are agreeing, yeah. So everything that is such that there is nothing there. So that if I had added those packets back in, it would be a vortex there, but now it's not. The other thing that is good now is that now, like these are in fact actually the same, and the configurations I'm calculating the probability for, like I have a bijection between them, because you can take one in the numerator and go to the same one in the denominator by just removing the vortex. And outside of that vortex, they should behave exactly the same. So if you think about that for a while, it means that everything outside will kind of cancel. You can fix what's happening on nu and then sum over what's happening outside separately. And then you get the upper bound E to the beta sum over all the packets that are in the support of nu. Then you only need to look at those. Omega or nu of p divided by, because the corresponding thing in the denominator doesn't have anything there. E to the beta sum over all the packets in the support of nu and rho of 0, because you don't have anything there. And this is in fact good, because if you're in support of nu and the group is set 2, that will be 1. So they will all be the same. Rho 1 is minus 1. So in the numerator we have e to the beta times a minus, because it's minus 1, and then times the size of the support of nu. And down here, we're dividing by something, and essentially what we're dividing by e to the beta support of nu. So we have essentially the same term everywhere, and that will be e to the minus 2 beta in total times the support of nu. So the likelihood that we see a particular vortex at a particular spot becomes exponentially quick in the size of that vortex. So that kind of confirms this idea that vortices should be very small when the parameter beta is large.
So that inequality, is it actually equality?
That one is an equality.
The last inequality.
Yeah, that's actually an equality, right? So the only inequality step is that I'm potentially skipping a lot of things here because I'm only summing on the ones that are 0 at the support of the vortex. But this is something I can do. And this proof is not that novel. It's essentially the same thing as you do for many other models, such as the Ising model. And it works in exactly the same way. Or you can do the same thing for the Ising model if you wonder how large a cluster could be. So before we take a break, we're just going to take this one step further, because this was for a particular vortex. What we kind of want to say in the proof is that it's quite unlikely to see a vortex, any vortex, at a pocket kind of all together. Because that's what we really want to know. Not only that it's unlikely to see a particular one. So with this result, we can very easily prove that the probability that there is a vortex and is a cluster of packets with support or in or at a given packet P, like your favorite packet. If you want to upper bound that, we should sum somehow over the sizes vortices can have. And then we want to sum over preferably the number of vortices you can potentially have at T with size K times the probability that you see such a thing, and we have that up there. So e to the minus 2 beta, and we have to be slightly careful with the support now. I mean, it doesn't matter when we get the scientific thing anyway, but if you have support in, since you have both positively and negatively oriented packets, you can always only have support at an even number of things. So let's write 2k here. So if we can upper bound this somehow, we would get some kind of exponential thing. We also need to think about how small vortices can be, but it turns out you can show that the smallest possible one you can have is the one where you start from one edge and take everything around that. Because in 3 dimensions, for example, the smallest cycle you can make is one with 4 edges. So if we assume the dimension is 3, then this would go from 4 to infinity. So this could be kind of fine and show that vortices were typically small. It can just show that this is not, it doesn't grow exponentially fast. But now we said that if you're a vortex, you're connected in some sense, and the sense in which you're connected is that you're connected to a set of packets if there is like some 3 cell that has 2 packets in its boundary. So if you wonder how many vortices you can have, you need to think about in how many ways you can make such clusters. And we don't really need a good bound now, we just need a upper bound. and they need to be connected, and connected structures in, say, graph theory typically have spanning trees. That's usually the easiest way to think about it, or a spanning path. So you should be able to start at some paquette and kind of go around in this vortex, visiting each like pair of paquettes most twice, and find such a spanning path of length 2k if there is k paquettes. And that needs to be a path in the lattice in the sense that you start at some paquette and then you go to some other paquette which shares a 3 cell with the first one. So then you need to think about how many paquettes are there that share a 3 cell with the paquette you started at. And if you have a paquette, and assume the dimension is 3, there are exactly 2 3 cells you could go to, or 2. So 2, and in each of those there are 5 paquettes, which is not the one you're currently at. So 2 times 5, and then this spanning path can have length, or need to have a length at most 2 to the k. E minus and then 4 beta k. So you have some kind of thing here, which is exponential, but if beta is large, it's definitely killed by that exponential. So this is smaller than e to the minus c times 4 times some constant, some constant times beta. If beta is large. So if beta is large enough to kill this term, it will kind of be small. So that says that the probability that you see a vortex at some paquette will kind of go to 0 quickly if beta is large. So it's really a kind of plasma of very spread out vortices. But now we need a break, and we need coffee, and we need sunshine.